All right, welcome to today's webinar about improving Moose workflows through Coreform Cubit. I'm Matt Cederberg, I'm the Coreform CEO, and I'm really excited to talk to you today about this work that we've been doing for the last few years. We'll just wait a minute for everyone to join. It's always fun for us to have some sort of human connection with you before the webinar starts. So if you are up for it, feel free to type in where you're watching from today in the chat panel, and we'll just greet you, and then we'll start the webinar. So I'm from my basement in Lehi, Utah. My co-presenters today, Clint Nicely, where are you from?
I am operating out of Dallas, Texas today.
All right, and Andrew Slaughter, where are you at today?
Shelley, Idaho.
Great. Okay, I've also got Greg Vernon on the line as well. Greg, you are in I think Springville, Utah.
That's up against the mountains.
Great. Okay, well, Jessica, let's go ahead and start the recording, and we'll get started. Clint, you go ahead and advance the slides. So again, welcome to today's webinar. I'm again Matt Cederberg, CEO of Coreform, and today the presentation will be led by Clint Nicely, who is a new hire at Coreform, who's recently spent 8 years at Raytheon, and Andrew Slaughter, who recently joined Coreform after 8 years at Idaho National Labs. So the agenda today is we'll be introducing some Moose workflows that we've added to Coreform Cubit. A lot of these center on isogeometric analysis, and so we'll introduce what IGA is. We'll talk about the new IGA Moose capabilities that we've added in conjunction with INL, and a special thanks to Roy Stogner and team at INL who've helped us with that. We'll talk about some other Coreform Cubit Moose developments that we've been working on, and then mention how some opportunities we have for you to get involved and test this and provide feedback. So with that, let me turn the time over to Clint. Before I do that, a couple of housekeeping items. Just if you've attended with webinars before, you know that you can ask questions throughout the webinar. In the Q&A panel, we'll answer them back. This webinar is being recorded for the future. First of all, we assume that all of you are familiar with Coreform Cubit, but if you're not, it's one of the best hex meshing software in the world, often used for advanced meshing for challenging simulations. It has a lot of functionality for CAD import and cleanup, hex meshing, a lot of Python scripting. We've recently added capabilities for isogeometric analysis pre-processing as well. And some of those are what will support the Moose nuclear simulation workflows, and that's what we'll be introducing more today. So with that, I'll turn the time over to Clint.
Hey, thank you. So yeah, thank you. I'm excited to be here. Hope you guys are all having a great time this morning. This will be my first webinar, so bear with me as I walk you through this. And please, again, don't hesitate to ask any questions in the chat. We'll get to you as soon as we are able. So introduction to isogeometric analysis. I'm not sure if any of you are how read you are on this topic, but isogeometric analysis is a functionality that's sort of an evolution to the technology that has been underpinning our structural analysis and any sort of analysis that you've needed to do that's used a finite element approach. And the difference between IGA, which is the shorthand for isogeometric analysis, and FEA is essentially that IGA uses the same inherent technology that we use in our CAD structure to underpin the element basis functions for a new finite element approach. So with that comes a couple of different benefits that we can now get sort of CAD accurate geometry in our analyses that no longer have to be approximated by basic building blocks like hexes or tetrahedra or triangles or cube or blocks. We can use actual splines to represent those curves. And part of my history in coming from this is I spent I consider a few years actually investigating this technology from Raytheon as part of my job duties there as a structural analyst. And what really brought me to understanding and desiring to use isogeometric analysis was that it represented a way to analyze components CAD geometry without compromising on the details that sometimes matter a lot in your design. And those details can be fillets, they can be tiny little features that are critical to the functionality of your design, but only take up a very small space in it. And because of that, these things would often be simplified or idealized to simpler geometry. And the promise of isogeometric analysis is that you can model it in your analysis as you see it in your CAD. And that's what our goal here at Coreform is, and that's what we're trying to bring into Moose as well. So the functionality of Moose currently, as we're here today to introduce you, is a body fit spline functionality in Moose. So now today you can run isogeometric analysis in Moose using a spline-based input for your input deck. So that's what we're showing here. Right here, this is a body fit, what we call a body fit mesh. This is on a quarter symmetry of a piston, and it's been idealized here. Some of these things have been simplified because in a body fit mesh, you still need to simplify things in order to get it to be meshable with hexes. Of course, there are additional ways that you can do this as we at Coreform are trying to bringing to isogeometric analysis, and that is a traditional immersed approach where your discretized mesh is surrounding your body. And of course, there can be levels all in between as you need it, depending on the level of effort you want to put into putting and building your mesh. So with this, it gives you better control and accuracy over your solution and over how much time you want to spend on your model prep. So why Moose? So it's a great question. So Moose is a fantastic platform to begin putting in and begin building IGA in. So right now, the nuclear industry can really benefit from IGA because of the details and the accuracy that IGA lets you bring into your analysis. The modern architecture of Moose can help us maximize the IGA benefits. We've also seen a very responsive partner in INL. Matt mentioned Roy Stogner, who has been a crucial component of helping us get isogeometric analysis into Moose. We also see that Moose is a growing platform for analysis, and the community around it is not only utilizing Moose, but also helping it to grow. So it's a really nice environment to help to put in isogeometric analysis, get more people familiar with the capabilities of IGA, and to have them use it and benefit from it. We also see that Cubit is also used widely by the Moose community. As Matt previously spoke about Cubit a little bit. Cubit, originally developed by Cindy National Labs, it was originally only really used for government analysis, but since then it has been pushed out. Trellis was the commercial form, and then Coreform has taken stewardship of the commercialization of Cubit, and it's now just called Coreform Cubit. Of course, we do offer Coreform Cubit Learn licenses, which are free to use for non-business uses, for personal use, or for research use at home. So we have all of these things, and that's sort of the building blocks of why IGA and Moose in particular was a really promising start to get IGA in there. So part of our ongoing efforts for Moose, we've been working with Moose and its community since before the 2020s. In 2019, we've been adding IGA functionality to Moose. We've been also in the past few years integrating Moose input deck building capabilities into Cubit, as well as other features that we are also adding into Moose, such as additivity. And in the future, we're looking to expand our Cubit capabilities with not only putting in a post-processor ParaView, but also allowing it to be cloud-based as well, so that you'll be able to access it through your browser, wherever you be. So part of the goals in these capabilities that we're adding in is that we want to have improved time to solution. We want you to be able to prepare, analyze, and get your results faster and more efficiently than your current workflows. We want to minimize the pre-processing time and the time that you spend troubleshooting for your Moose codes. We want to improve accessibility of Moose to non-experts. And we want to also provide a unified pre-post solve user experience, kind of like an all-in-one CAE environment. So all of these goals are really what are pushing us to go for and adding these capabilities and extending all of these possibilities to the Moose user base. So here are some, just a little bit of the details of what we added to the Moose user base and its ecosystem. So one of the first things that we did was we added specification of the Bezier extraction to Exodus files. So if you wanted to use IGA, right now you need to use a Bezier extraction in an Exodus file, and you load that Exodus file into your input deck. This is right now done in Cubit. There are other ways that it's possible to build this, but for the purposes right now, we feel it's easiest and most straightforward now to do it through Cubit. Another capability that we've added in ParaView actually is ParaView. We've made ParaView capable of modeling the Bezier elements within its architecture, so it can pull up and it can visualize Bezier elements. So you can now build Bezier elements into Exodus. You can look at them in ParaView, and you can also now have Bezier extraction in libmesh as well. So these are all the building blocks that we need to get it to the point where now we can have isogeometric analysis and the Bezier extraction in Moose. All these things were part of our efforts to bring you isogeometric analysis. So we've spent a lot of time on building isogeometric analysis. Now let's sort of get to the basis of why you're here. You're here to learn about what IGA does in Moose, how it performs, and to get your hands on. So let's take a look at just a first simple problem. Arguably, I'd say it's one step above an academic problem, but these are steps that needed to be taken in order to understand the convergence of the Moose, the new Moose IGA elements, and how it functions. So you need to get a good idea of that. So in order to get a good feeling on how it works, we need to look at a simple problem, and that simple problem for us in this case was a cylinder under internal pressure, which is a problem if you went to any sort of engineering, mechanical, civil, engineering undergrad. This is a problem that you've seen before. You've solved this by hand. It's fairly standard and is great to use as a benchmark for capabilities and understanding the convergence rate of new computational methods. So in this case, we have a cylinder here that is 9 meters internal radius, 10 meters external radius, and is put under pressure of 10 pascals from the interior. When you look at the analytical solution provided here, that's sigma t. When you put all those values in here, you can come to the maximum stress is given to be about 95.26 pascals. In this plot, we can see that we also have the stress distribution through the thickness of the cylinder as well. So we run through this analysis in our Moose with increasing levels of fidelity for our mesh. And these are the answers that we get. And we get some very nice answers here. We'll walk through this. So the top right plot is just a hoop stress convergence. We're looking at just a straightforward element count in this place. And the IGA result, which is a blue line, which is a little bit hard to see because it's obscured by the analytical solution line. But the IGA solution is being compared against a first order hexahedral element and a second order hexahedral element within Moose. So we see from this right off the bat, you can a good eye can see that the isogeometric analysis converges very quickly to the analytical solution, and in fact, its answers lie almost on top of the analytical solution. The second order hexahedral does a very good job, but it is slightly stiffer in its representation of the pressurized cylinder and gives a little bit higher stresses. Still very good, but slightly higher. The first order elements, they're doing the best they can. First order elements always need a very fine discretization to get a converged answer. So this is not surprising. If you look at the second plot that we have here, we have this convergence expressed in a different way. Now, isogeometric analysis uses fewer degrees of freedom than a typical finite element, than an equivalent element count would be for finite elements. So in this case, we are showing the convergence of the isogeometric analysis with respect to the finite element second order. And here we're not measuring the stress, but the relative error that they have with respect to the analytical solution. And this makes it really kind of clear how much more accurate the isogeometric analysis method is with respect to other computational methods. So here, again, we see the finite element analysis second order. Very good. It's less than 0.5% off, but our IGA, once it's converged, is on the realm of 0.01% away from the analytical solution. So it's doing a fantastic job for the level of discretization that it's seeing. And in fact, we see that it converges to that solution sooner in the terms of the degrees of freedom than the FEA second order does. Another thing to note is, I had mentioned this earlier, that one of the benefits of isogeometric analysis is that we are able to represent our geometry exactly as it is inside of the CAD definition. So this image here of a stress distribution, which is out of pair view, this is a circle, or the cylinder, that is meshed with only 8 elements around the circumference of the circle. If you were to do this in a finite element method, this would look like a octagon instead. It would not be a circle. It would be something that would be a multifaceted approximation of a circle. So that's something that isogeometric analysis is able to capture at even very low resolutions, is the exact geometry of the component that you're looking to analyze. So let's step it up a little bit. Let's look at something that's a little bit more interesting, a little bit more complicated. Now that we know how hoop stress functions, we're able to take a look at a more complicated problem. So in this case, this would be a simplified reactor pressure vessel, or sort of a large propane tank. In this case here, we've run this run was run by Ben Spencer, but here we can even see that for this case, these results are sort of showcasing the differences between a Lagrange approach and the Bernstein approach, which are Bernstein elements are IG elements, and Lagrange elements are, of course, the finite element analysis elements. So the plot that we're looking to align to here are the 1D second order Lagrange fine element, which is right here, starts at about 1.5 and goes down in between. So it's this middle line. We can see here that there are lots of different approaches, and they're all sort of in the same range. One thing that we'd like to note is that as you get a finer distribution, you can get closer to the answer that we seek. It is one of the things to note here is that because of the IGA elements, we're not changing the answer. The answer is still the same answer that we speak with that we're trying to seek. IGA just might get there a little bit sooner in its convergence plot. So for these guys, we do see a lot of the IGA elements lying on top of the same solutions that we're getting for the finite element analysis, which is great because we don't, it shouldn't be that IGA changes your answer, just gives you a more accurate version of it sooner and more efficiently. So here's another verification problem that we're kind of going through. Again, this is a more complicated type of stress here. This is a sort of a C-frame press. This is a mechanical component that we would use to press ball bearings into place. We're looking at the maximum principal stress here inside of the curvature, at the center of the curvature. We're seeking the max principal stress there in that location after we apply an interior load here pressing open the C-frame. So when we look at that sort of analysis, again, we get similar results that we had seen before. Again, first order, it's doing it the best it can. We do see IGA and FEA second order elements. They do closely align to the same level of convergence, with IGA getting there a little bit faster in terms of degree of freedom. Over on the left, we do see an image again. This is a coarse representation of the C-frame, and again, just to keep on hitting on this, but this is a coarse representation. If you were looking at this with the finite element, there are only 3 elements through the quarter circle, 6 elements through the entire one, through the entire bend radius there. It would not be a smooth transition with a FEA approach. So this is, again, we are capturing the exact CAD geometry as we are looking at here. And of course, this is a body fit geometry, so the fillets did unfortunately have to go away. But we are working on trying to make sure that we can involve some sort of a immersed approach as we move forward. So let's see. Let's wrap up with what we've seen so far on our initial testing and evaluation of MOOS IGA. So one of the first ones that we've seen is that it gives us accurate geometry. So accurate geometry by the use of higher order spline elements. Again, even at very coarse discretizations, we can get exact geometry as it's represented by the CAD system as it was built. You don't have to have any sort of faceted approximations any longer. You also get efficient calculations. The isogeometric analysis will give you a more efficient result by converging to the solution with fewer degrees of freedom. So that being said, MOOS is in IGA. You can use it now, but it's not to be said that something can't be improved. Things are always looking to be made better. So in the future, as we move forward, we will look to optimize the performance of the isogeometric analysis implementation within MOOS. We're also looking to add higher order IGA elements. Currently, there are first and second order IGA elements available in MOOS. We are hoping to increase that to third and higher so that you can get even better levels of efficiency and converge sooner using higher order elements for your discretizations. We're also looking to add hierarchical splines, which enables you to add a level of local adaptivity to your analysis so that you don't have to do a blanket dense mesh or a blanket coarse mesh and try and really put some sort of like rigorous hand-based biased mesh on there. The hierarchical splines will really let you have a local additivity that doesn't require as much input from the user as defining a hard to find biased mesh. Improved quadrature routines. So always looking to improve and increase the solution and efficiency that we get in trying to seek out our results. And then of course, one of the things is we'd like to do is we'd like to reduce the time that you spend meshing. So that's partially what we had mentioned previously, where we have our Flex IGA approach, and that this allows you to ensconce your component within a discretized mesh, and that discretized mesh will do the analysis on the body that you're hoping to analyze. And this allows you to have fully featured components inside of your analysis without any idealization or simplification. So here's an example of a hierarchical splines with that local additivity. This is a sort of an open hole in a plate. This is a quarter symmetry. And you can see here that this is the base discretization on the left, and on the right is after the hierarchical splines with additivity has been applied. It applies the splines around the features that are needed, and everywhere else it just leaves alone. In terms of the capabilities for the Flex IGA, for the immersed cell, this is an example that we've run within our own Coreform IGA that we hope to be able to bring these same capabilities over to Moose. And that is to, again, we want to increase the efficiency and make it easier for the users to mesh their components so that they don't have to choose what parts of their components they aren't as interested in getting results from. It should be that we're interested in getting results from all of our components and not just parts of it. So the flex meshing approach allows us to do that, and we can hopefully we will get this functionality into Moose as we are building it. So again, like I said here, as we mentioned earlier, we have all these different approaches. We have the full body fit, full immersed, and we have areas in between where you can choose to have body fit in some areas and immersed in others. And it's flexible in the way that you can choose where the meshing is, where you want it to be and how you want it to be. So you can, it's truly up to you, still up to the user. If you like your current workflow, you can stick with it. If you like the flex workflow, you can save time and allow yourself more time for other tasks.
Clint?
So, yeah.
Yeah, if I could just cut in, so to emphasize what Clint's mentioning. So today, obviously, we've got the body fit mesh in Moose, and we're interested to have people start trying that out with this with the flex spectrum with this traditional immersed workflow. One of the reasons that we're hosting this webinar today is we're looking for motivating examples of hard to mesh components and parts that you have as we're about to embark on this next stage of development of IGA and Moose. And so we're looking for these motivating examples and hoping to get some of them from the Moose community today.
Yeah, if you guys have fancy geometry that has all sorts of fillets and curves and things that makes you bang your head against the wall, we would love to see it. So this next section deals with our work in building a Moose editor for within Cubit. And Andrew, I believe this is your territory.
Yes. So I'm just going to speak for a few minutes about workflow with respect to the user experience, not necessarily the IGA technology behind it. So next slide, thanks. So if you're using Cubit to build these types of meshes, we hope that we can use Cubit to prepare your inputs and analyze your outputs all within one interface. So not only will we'd be able to improve efficiency and accuracy with your simulation, but hopefully improve your workflow in general by giving you a single tool to use. So there's some initial features in there now. If you'd like to go try them out, it's possible to get the Moose editor enabled. It's what we would consider an alpha phase, just some basic capabilities are in there, but it'll be moving fast in the next few months in improving capabilities in general. Next slide, Clint, thanks. So this is, here's a quick demo of kind of what's in there now. It's pretty familiar if you've used some of the other Moose editors that exist. It's autocomplete, some error checking, things like that. So we have the basic infrastructure built, but this will continue to improve. The main thing that we will be adding soon is integration with the Cubit geometry. So you'll be able to select items on the geometry and they would then be added into your input file. Or if you select an item that's already in your input file, it would highlight the geometry in the Cubit window as well. So hopefully it will help you navigate your inputs with respect to geometry in a clean way. And this is it. This little bit here is showing off a templating feature that will be in there as well. So if you have fairly standard input files that you're running and maybe change a few parameters, you can load in a template, and this will make sure that all pieces of that template then are properly filled out. So next slide. So this is the roadmap. So like I mentioned, we have some core capability in there now. That's the syntax checking and autocomplete. Coming up for our June release, we'll be adding increased syntax highlighting, lookup, and the big one there is that third bullet, a unified tree and text editor. So we have other ways to edit inputs in Cubit that we're working on that are more, I guess, would be automated. So you don't have to type out all the brackets and things like that you would in a traditional Moose file. And that editor would be exposed to the Moose syntax as well. And then, so you'd be able to edit in either interface and they would both keep up to date. And then I already mentioned the geometry selection lookup, which will again work in both flavors of the editor and hopefully help workflows. And then as we continue at Coreform, we'll just hope to add more capabilities, including result visualization. That's the pair view plugin that there's a slide coming up about. I mentioned the template. A big one will be multi-app support. That'll be a nice feature. If you've used Moose multi-apps, you have multiple input files. Cubit will understand that these input files exist and can do some autocomplete and connection between those input files. And you'll be able to run your application directly inside Cubit as well. So next slide. Another one more about the future. And this is the technology we're building this upon. It's web-based technology. And that's really being motivated by implementing a Cubit version that's hosted on the cloud or and usable in your browser. It'd be a familiar experience that you have now with Cubit, but using modern web technology, and potentially even be hosted for computation on supercomputers, or perhaps your company's computer and things like that. And as well as in that workflow, their pair view would be available for all your post-processing needs. So in the end, we're on the path to build a very powerful tool with respect to simulation, but also with respect to workflow and user experience. And so if you're interested in the workflow concept, just like we're looking for complicated geometry, we're interested in workflow improvements as well, where Coreform could help you out and make your life a little bit easier and more efficient. I think that's my job, Clint. I think I'm done.
Yep, that's it. And I think that's getting us pretty close to the end of this webinar for the prepared version of the webinar. So again, if you guys, the reason you're here is because you're interested in isogeometric analysis, feel free to join the IGA wave. There are multiple ways that you can begin evaluating this feature. You can contact us at Coreform to help you get started. You can also use the Moose discussion forums to get you started. Lots of people are here ready to help you get Moose installed and Cubit going to help you get these new IGA workflows going, look at your complicated geometry and help you get make sure to streamline your workflow.
Great. Well, Clint and Andrew, thank you so much for the presentation. It's a lot of work that's gone into this the past few years, and again, thanks for presenting it so well. We have time for some questions now. So as you have questions, you can type them in the chat panel or in the Q&A. Looks like the first question that we've got is, how would we get our hands on this to test IGA in Moose? Andrew, maybe you could give some insights into that.
Yeah, the basic capability that Clint showed at the beginning with the body fit methods is already there in Moose. It exists now. So if you update your Moose and update all your conda dependencies, you should be able to run some test problems right off the bat that are included. So if you're familiar with Moose, if you can run the test harness with regular expression IGA, you'll see the tests, and they should all pass. And if you have a problem with that, you can throw it up on the forum, and we can make sure that your system is set up correctly. There was just some changes with respect to output in VTK that were just merged recently, like the last several hours or days. So hopefully they're all available to people, but if not, we'll help you. We'll get it fixed up.
Okay, thanks. Here's another question. The text editor and the model tree that are being built, are those usable for other codes or just with Moose?
That's me again. So yes, they will be available. Well, not other codes. They will be available for Coreform's IGA solver that Clint also demonstrated with that flex solve on that pressure tank. But I think the plan is to be able to open it up to other things as well long term. So if there's something of particular interest, we would be interested to talk to you about it.
Cool. Great, thank you. Let's see. Let's see if there's some other questions that have come in. Let's see. I think that's all the questions I've got so far. So we'll just hang in line for another few seconds and see if any others come in. Okay, Ian, well, we're waiting for that. Just, I'd like to tell everyone thanks for thanks. It looks like there's one coming in right now. Thanks for attending. We're very, we mentioned we've been involved in the Moose community for a few years now and have it's been very interested with all of the developments going on. Our intent and hope is to have Coreform Cubit become the default preprocessor for Moose. And so we've again made available the Coreform Cubit Learn Edition so that anyone can use it for free for non-commercial use. And we also have, again, Coreform Cubit for commercial use and then Sandia Cubit for government use. So the idea is that this should be usable and make Moose more accessible across your organizations to push wherever is needed for FEA or IGA. Okay, here's another question that's come in. In the Cubit interface to Moose, with its autocomplete syntax, what are the capabilities with respect to consistency checking? For example, if one has specified a variable of a certain type, will there be constraints on the kernels that are available?
That's there will definitely be some level of consistency checking that we can do based on the language itself that Moose dumps, the schema, I guess you'd say. And also by running Moose, it reports back errors. But if certain kernels are restricted to certain elements, that's actually a Moose level check that would be needed to be made. So that's really would be outside of what we have access to in Coreform without changing Moose, which could be done obviously because it's open source. So that's more of a Moose question, but I'd happy to field that if someone wants to reach out to me. We could talk about your specific needs and relate to the proper people at Moose if there's some checking you need with respect to your kernels.
Yeah, and so Andrew, on that, like, at least for now, as far as the autocomplete syntax, I know that we rely on, if a user's built a Moose app, they can spit out the allowable syntax. So I would imagine that this is something that we could do. It may be dependent on a user providing a path to the Moose app that they're wanting to run. But I would think that we could hook into their Moose app to run those checks.
Oh yeah, that's what I was speaking of, like the basic checks against their applications. It's the JSON dump, we would call it in the Moose world. That exists, but to my knowledge, there's no specification in that input file to limit element types. You'd have to program if your kernel's programmed properly within the valid params function to limit element type, then that probably works right now. But I'd have to see a specific example of what this person's asking. But what they're asking for is probably not very difficult if it's not already there.
Great. Thanks, Andrew.
Yeah.
Here's another question. Will the web-based development be for Moose only or made available to generic Qubit? Yeah, so the web version of Qubit that we're developing, it's early days. So we've started adding new UI components in JavaScript. And so eventually over the next, probably over the course of a year, we'll be working on this. But this is for generic Qubit. So it will absolutely work with Moose. This will be available for general Qubit use and as well as to connect with other solvers. And so if that's something that's interesting to you, we'd love to talk and make sure we take your interest into consideration as we develop that. So here's another question. What language is the syntax checking done in? Is there an API to it? We're thinking of doing a project related to Moose input checking consistency ahead of runtime, a wizard input generator type of thing, and don't want to duplicate work.
The editor itself is going to be written in TypeScript and JavaScript, and so all of the checking utilities are going to be written in those languages, but it's designed for that kind of use case in mind. It's all based on JSON, what we're calling schema files that kind of indicate what's possible for your input. So I think there's probably room for collaboration or on that front. So we would be interested in what you're doing and how we could help.
Okay. Great. I think that's all the questions that have come in. So I'd just like to say thanks to everyone who has participated in the webinar today. Again, the recording will be up on our website, and hopefully we'll look forward to seeing you interacting on our forum and the Moose forum as we continue to push forward with this work. So thanks again for attending, and hope everyone's has a great day.